Hello, my name is Aaron Hope, and today we'll be discussing bond line structures in organic chemistry. These structures are the blueprints of any molecule. They describe the spatial arrangement of atoms in a molecule. In other words, they describe how a molecule looks. In order to discuss bond line structures, first we will consider the shortcomings of condensed and expanded formulas. Then we will apply three basic steps to transform an expanded structure into a bond line structure. Finally, we will consider how this structure is useful to chemists. We know that atoms are the building blocks of the world around us. Moreover, the way that these atoms are connected are the fundamental reason that molecules differ. What we need then is a way to systematically describe these molecules so that their spatial arrangement can be determined. Consider this chemical formula, C2H6O, just like you'd see in high school chemistry. What does this really mean? All it tells a chemist is that they are dealing with a compound consisting of 2 carbons, 6 hydrogens, and 1 oxygen. Unfortunately, this could be more than one compound, such as ethanol, seen at the top here, and dimethyl ether here. In order to distinguish between these molecules, we could use an expanded structure like the ones pictured on the right. But as you can see, they can be quite cumbersome to examine. Thus, we need a way to distinguish between these two compounds that is both detailed and simple. Let's consider ethanol, pictured here. We can see how the atoms are connected, but even for this relatively simple molecule, the full drawing can be messy. This gets even worse when we try to draw out how this atom looks in three-dimensional space. In order to pare down these drawings, we can see that there are lots of carbons and hydrogens. This is a common theme of many organic compounds, from gasoline to painkillers. Therefore, what we want to do is develop a shorthand notation for these two atoms. When we look at ethanol, we can start with an expanded structure pictured here. There are 3 basic rules to drawing a bond line structure. First, we will erase all hydrogens that are attached to a carbon. Next, we will erase all of the C's for carbon and replace them with dots in the same place. Finally, all we must do to create a bond line structure is to connect the dots and remaining letters according to our expanded structure. All lines will make angles of 120 degrees, as you can see here. What results is a drawing of ethanol that tells a chemist everything they need to know about a molecule, and which is much more concise in expressing this information. Now, ethanol was a relatively simple molecule, but we can apply these rules to more complex molecules, such as nonane. Again, the formula gives us no useful information, and expanded structure is incredibly bulky. However, simply by applying the 3 rules of bond line structures, we can reduce nonane to this bond line structure, which is much easier to present. To check that this structure really is nonane, simply count each vertex on this zigzag and make sure to include the endpoints. We can see that there are still 9 carbons and that all the hydrogens are implied. These structures, while simple to grasp, have huge implications for organic chemists. They allow us to illustrate chemistry in a way that is detailed without being unmanageable. In fact, you may consider bond line structures to be the language of organic chemistry, allowing chemists to communicate abstract reactions with elegant visuals. For more information on bond line structures and organic chemistry in general, I highly recommend Khan Academy. Thanks for listening.